Alright, in this video we're going to talk about inverses, and this is going to build a little bit upon what we talked about with one-to-one functions. So, if a function is one-to-one, then its inverse will also be a function. So the way you want to think about that is, if you have a function and that function passes the horizontal line test, that means it's one-to-one. If that function passes the horizontal line test and is one-to-one, then its inverse will pass the vertical line test, therefore making it a function. Okay? What you look at with a function and an inverse function is that essentially the x's and y's will switch. Okay, so the domain and range get flipped, and you have a new function where the x's become the y's and the y's become the x's. So this first few questions are really easy. If I want to know, if I know that a function, when evaluated at 1, gives me 5, what is the inverse function evaluated at 5? Well, the answer to that would be 1, right? So it's x and y just flipped. Similarly, if f of 3 is 7, then f inverse of 7 would be 3. And if f of 8 is negative 10, then f inverse of negative 10 would be 8. Okay, so the x's and y's are just switching between f and f inverse. Okay. If f is a one-to-one function, then the inverse function f inverse satisfies the following cancellation properties. So what this means is, if I do function composition, so if I take two functions that are inverses, and I compose those inverses, if I end up with just x, okay, nothing else but x, just x, by composing it both ways, then yes, they are definitely inverses. So we're going to show that below here. So we want to see if f of x, which is x cubed, and g of x, which is x to the 1/3, I want to know if those are inverses. So what I'm going to do is I'm going to do f of g. F of g would be, okay, take the function f, which is x cubed, and instead of x, plug in the function g, which is x to the 1/3. And x to the 1/3 to the third, I would multiply those exponents, and I would just get x. Also, if I did g of f of x, it's going to work very similarly here. I take the function g, which is x to the 1/3. I plug in the function f, which is x to the third. I use my exponent property there and multiply those, and I get x. So the idea is, because when I compose them both ways, and I just got x as my final answer when I simplified those compositions, that shows me that yes, f and g are inverses of each other. Alright, so the meat and bones part of this is, how do I find a one-to-one function? How do I find its inverse? Okay, so if the function is one-to-one, then I know that its inverse will be a function. And how do I find that? And I'm just going to follow these 3 steps. Okay, so it's the same steps every time. First of all, I'm going to, instead of f of x, I'm going to write y. Y equals 3x minus 2. The next thing says solve the equation for x in terms of y. So what I'm going to do is I'm going to get x by itself. So I would add 2. So I would have y plus 2 equals 3x. Then I would divide everything by 3. So y plus 2 over 3 is equal to x. I have solved for x in terms of y. Then what I'm going to do is I'm going to switch x and y. Interchange x and y. That does not mean I need to solve for anything. All I'm doing in that step is I'm literally just taking y and x and switching those. So that's going to give me that x plus 2 over 3 is equal to y. Okay, just switched x and y. Then the resulting equation is y equals f inverse of x. So then I can say, instead of y, I can say that f inverse of x is equal to x plus 2 over 3. Okay, so it's the same process every single time. Y equals x to the 5th minus 3 over 2. Solve for x. So if I go about solving for x, I would multiply by 2 to get rid of this. So I would have 2y is equal to x to the 5th minus 3. I would add 3. 2y plus 3 is equal to x to the 5th. And then I would take the 5th root to get rid of the 5th power. So I would have that x is equal to the 5th root of 2y plus 3. These last couple steps, I think you can probably do them at the same time. You're going to change x and y, and then you're also going to, instead of writing y, write f inverse. But in this case, it's g inverse. So g inverse of x is going to equal the 5th root of 2x plus 3. Okay, that's my inverse function g. All right, and I'll do one more example. So h of x, again, I'm going to replace this, or write it as y. Y equals the square root of x minus 2. Solve for x. So the first thing we'll have to do is square both sides. Y squared is equal to x minus 2. Simply just add 2. So x is equal to y squared plus 2. I'm going to switch x and y. And then instead of y, write h inverse. So h inverse of x is going to equal x squared plus 2. Okay, same steps every single time when finding an inverse. Follow those. As long as your algebra skills are good, you shouldn't have any problem finding inverse functions. One thing that I do want to show you before I stop the video is that a function and its inverse will always be symmetric about the line y equals x. Okay, so I'm going to look at this example we did up here. We know that x cubed and x to the 1/3 are inverses of each other. I already have graphed the line y equals x. Okay, so y equals x is going to be my line of symmetry. If I look at y equals x cubed, and then I also look at y equals x to the 1/3, notice how those two graphs, the blue and the green, are symmetric about that line y equals x. Okay, if I continue to zoom out here, you'll see that that's always true. They are always symmetric about that, that diagonal line through the origin with a slope of 1, y equals x. If you tested that with the 3 inverses that we just found down here, with those original functions, you would see that that is true as well. An inverse function will always be symmetric about the original function, symmetric about y equals x in comparison to the original function.